Hello, welcome back. This is Gradient Descent tutorial part 2. My name is Chieh from Northeastern University. So from the last video, we did a simple example of gradient descent with this solution. So this is the equation for gradient descent. What we did is we made an initial guess of x naught. If you remember, we set x naught equals to 3. So then we look at the derivative of at the location of our guess. From that, we get x1. And with x1, we get x2 in using the same approach. And eventually, at xn, there's basically no change. So it has converged into the right answer. But like I mentioned, the calculus approach appears to be much easier. And the reason for this, for this video is then we want to talk about why. Why do we want to use gradient descent then? Well, that reason is because we showed you a very simple example. Like this is the calculus approach and it seems very straightforward. But in real life, you will actually get really, really messy equations. And this right here, this is not even that messy. This is like a part of a Gaussian. And this equation where x is some like vector, right? And a is some n by n matrix. Well, if you were to find a derivative of this, you'll end up getting this function. Now, how are you going to go about solving for x? Well, it kind of gets complicated. And very often, there are many functions out there that you just can't solve for x, and it's very difficult to solve for x. So, since it's difficult, this is why we do things such as gradient descent. Instead of solving for x, what we could do is use gradient descent as an estimation. To estimate it by inching closer and closer towards the true solution. So let's say we have this example here, right? If we have this example and we'll let A equals to this matrix, sigma equal to 1. So this right here is just 1. So we can kind of ignore that. Now, if we find the derivative here, I don't know if you remember how to find a derivative, but if you have e to some function of x, the derivative of that is e to some function of x, and then the derivative of the function of x. Now, you might not remember how to find the derivative of this. So, like, derivative of this top portion, if you write out the x in the vector format, looks something like this, okay? And if we multiply them out, it's equal to this. And what we do is we take derivative with respect to x and with respect to y. Okay, so once we have the two derivatives, notice how you can take out x1 and x2, x1, x2 to form x1, x2 and the matrix. Now, you have this. This is the same written this way. Now, notice this is just A, right? See? A here, A here. This is just A. And this one's A transpose. A plus A transpose. And then this is the X. And that's how I got this equation here. A transpose X. So that's, in any case, that was just a quick review on how to take the derivative of a vector. And now that we've done this, we can write this out. And it's pretty easy to solve this using gradient descent. If you were to try to solve this same thing using calculus, it would be kind of complicated. Now with gradient descent, we have the derivative, right? So all we do is we make the initial guess. So initial guess x0, we can just say like 1, 1, for example. Whatever, you can guess whatever you want. Oh, wait. Oh, yeah, 1, 1. And then you put this derivative in here, and you just keep solving it like the same way we did in the last video. Of course, we'll still set alpha at 0.2. And if you were to do this over and over again, I actually did it out. At roughly x equals to 50, if you do it 50 times, you'll get the solution 0, 0, which is the optimum solution. And it kind of makes sense. Now, remember, we're trying to maximize, okay? So we're trying to find the biggest one. And this right here kind of looks like a Gaussian distribution. And if you remember, a Gaussian distribution kind of looks like this. So at 0 is where it's max. And therefore, even in the higher dimension, 0, 0 is still the max. Now, what about this alpha value we were talking about? Alpha. Well, you might have noticed the alpha value right here provides the size of each jump, right? You can either jump this big or you can jump much bigger. Then that depends on alpha. If you have a large alpha, it jumps much faster. If you have a small alpha, it jumps slowly, 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 like that. Now, it's good to have a large alpha because you get to the solution faster. But if it's too big, it will cause you some problems. Now, let me show you, right? If you have a large alpha, you cannot converge. So let's say you jump here, and then you jump here, and you jump back, and you jump back again. So you can never really reach this point. So if you have an alpha that is too big, then you have a problem. So my suggestion, there are many ways to get the alpha value, is that you start with a large alpha. I don't know, maybe like a 1. And then as soon as you notice some kind of overshooting, that like maybe it's getting worse, or it's in this like back and forth situation, in your code, you can kind of test for that. And if it looks like it's going back and forth or it's getting worse, all you have to do is reduce alpha. Do something like alpha is equal to 0.8 alpha. So whatever alpha it is, you make it a little bit smaller. And then you just keep reducing it until it was good enough. Because just because you reduce it once, it doesn't mean it was enough. You might have to do this multiple times. So you just basically put it in a loop, reduce alpha until this looks like this rather than something like this. Let me draw that again. You don't want this, like, because that just means alpha is too big. So if you just keep reducing alpha until you see something that looks like, I use a different color, like this right here. That's what you want. And eventually you'll find a small enough alpha and you can keep going. And that's basically the general idea of how gradient descent works. And yeah, I think in the next video, we'll talk more about other aspects. Maybe we'll do an example of this. So I will see you in the next video.